grade 12s, we are back to chemistry, and I can hear the groans from some of the boys because you'd rather do physics. I'm sorry, but we get into nice chemistry, and this chemistry doesn't have a lot of theory. And in fact, I like to tell my learners, if you can summarize rate and extent on one page, half a page even, then you've got all the theory, it's application. Okay, so you've got to listen carefully. Now, there's obviously a few key important terms that you need to know. So we've got 4 here that you're gonna hear often that we're gonna talk about today: collision theory, rates of reaction, catalysts, and activation energy. Those are the ones they can ask you to define. So I'm gonna give you 2 minutes to quickly discuss those terms and see if you know what they mean. And your 2 minutes start now. So how did you do, grade 12? Hopefully you were okay. Hopefully none of them are too new. We're going to talk through all of these today, okay? So don't stress about it. Now, first thing we're going to look at is, let's see how rate of reaction actually works. And remember, the whole thing about rates of reaction is we start with reactants. Those reactants give us products, and somewhere along the line we have to figure out how that happens. So remember, the reactants, if they go through effective collisions, and we can define an effective collision from the collision theory, that then gives us a product, and the products that they give us is known as the yield. Okay, the yield is how much product we get at the end, so that's quite important. And when we look at this, rate of reaction really tells us how much product or whatever we get per unit time. Rate has to do with time. So besides that, so we know we end up with this, we've got to look at what affects the rate, what makes it go fast or slower, and we're going to look at nature of reactants, temperature, concentration, surface area, pressure, all of those sort of things. And then, just for fun, we're going to put in a whole bunch of stuff from grade 11, because we're going to consider what happens with a catalyst, and of course a catalyst changes the activation energy, and of course changes a whole bunch of stuff like that. And then we're going to look at delta H, and whether it's exothermic and endothermic. Okay, so we've got a nice big overview. Let's jump right in there. Now, first of all, with the collision theory, there's 3 things that have to take place. Number 1, the particles have to collide. It's called collision theory. Number two, the particles must collide with correct orientation. Nothing we can do about that. They've got to collide into each other in the right way. And number three, they must collide with sufficient energy. That, of course, is our activation energy. Now, the whole point of that is if those things happen, so they collide with sufficient energy, and they collide with the correct orientation, they have what is known as an effective collision. And an effective collision, if we have more effective collisions, so a greater number of effective collisions, we have a faster rate of reaction, okay? And that is what we are trying to do. In this section, we're looking at what we can do to either lead to a faster rate of reaction, so we lead to a greater number of effective collisions, or we have a slower rate of reaction, so we have less effective collisions. And sometimes we do want to slow reactions down because they're just too fast or they're too violent. So we now need to decide, what does rate of reaction mean? So it's defined as the change in concentration of product or reactant per unit time. That's a definition, though we don't always measure it in change in concentration of reactant and product. We can measure it in other things, which I'll talk about in a second. So as an equation, my rate is change in product over change in time, or change in concentration over change of reactants over time. What that means for us, though, is because we can measure the rate of reaction in a lot of different ways, not just in concentration, the units vary. So the units we use depend on how we measure it, and that includes time. It's an unusual thing for us because we're so used to being told, well, the SI unit for velocity is meters per second, the SI unit for mass in physics is kilograms, the SI unit for mass in chemistry is grams, and now I'm telling you it doesn't matter because it depends on the reaction. But there's obviously certain things that we're going to measure it in. So we can measure, the units can be things like moles, so concentration per decimeter cubed per second. Could be per minute, could be per day. Heaven forbid we do something that slow. Could be per hour, but it could be a mass. So it could be grams per minute. Okay? It all depends on how we measure the rate, on the type of reaction, on both the reactants and the products, and the ease of measuring what's happening. Okay, so that means we've actually got to talk about, how do we measure rate? What do we look for? Well, there's a couple of things. Number one, we can measure how the reactions disappear or the products appear. Now, that can be a little difficult and a little tricky to measure and go, oh, I see them, no, I don't. That's a little more iffy, and that's a little difficult to put into a measurable thing. So that's more what we would call a qualitative way of measuring it. So we can look at it and we can judge. We can look at color changes. Color changes are great. We can use color cards. Color cards just mean it gives us a way of measuring the intensity of the light, or we can use what are known as spectrophotometers or photometers probably. I doubt any school has, maybe some school in this country has it, I know we don't. All that means is it measures the intensity of the light. That's a great way to do it. And we would do that for a color change reaction. So for example, zinc with copper sulfate. The copper sulfate will eventually go colorless. We can measure how slowly or how quickly the color changes, okay? The next one is concentration of ions, and there we will look at conductivity. There we could use a multimeter of some sort, where we look at how well or how badly the solution changes its ability to conduct an electric current. More likely, the ones that we're going to actually do, these are the two, is we're going to measure the volume of gas produced. Okay, so we use a upside down test tube. It wouldn't be a test tube, we need something with values on it. It would be an upside down measuring cylinder, something like that. Or so that's the volume, okay, so we can measure the volume. The second thing we can do is measure mass changes in a vessel. That's great with the gas. So what we do with that one is we actually put our vessel, we're going to do an example with it, onto an electronic scale, okay? A normal scale wouldn't help us. We put it on an electronic scale, and we allow the reaction to happen in an open situation, and what happens then is the gas is allowed to escape, and what we're actually measuring is the mass of the gas that's leaving. So these are the two we're most likely to use, all right, when it comes to equations, or if they ask you for practical ways of measuring stuff. Often though, if we're doing graphs, they're going to give you concentration, but that's okay. And then the last one is turbidity. Now, that's precipitate formation, and what that means is when you look at the reaction, because of the reaction between the 2 or 3 or whatever we put in, because of the reaction between the reactants, we get a precipitate. A solid is formed that's insoluble. It doesn't dissolve in the solution. And so the solution goes cloudy. So that's what turbidity means. It's that cloudiness. And if you have to leave it for long enough, you can actually see it settle and you'll get your precipitate at the bottom. The best example you're going to have with this is the reaction with sodium thiosulfate, which I'm hoping if you haven't seen it yet, you will see it at some stage. And how we measure that is we put the reaction vessel, because we use a solution of sodium thiosulfate, which is colorless, in a conical flask. We put it onto a card with a cross on it, and when we pour in hydrochloric acid, it gets a sulfur precipitate, which goes cloudy, and we actually watch until we can't see the cross anymore. That way, we can measure our reaction to the same place. So we know when we've got to the same amount of precipitate, because the turbidity is the same. It's one way of doing that, okay? That's also a difficult one to do at school accurately. Okay, so those are ways we can measure the rate in a practical sense. Now we need to discuss the things that affect rate. We're not going to get through all of this now. We'll take a break in the middle. And with all the things that affect rate, what we are trying to do is we're looking at what this change does to the number of effective collisions. And either it's going to make it so that we get more collisions, and the more often particles collide, the more likely to have an effective collision, okay? Or, and temperature is where we start, if we change the temperature, we change the energy of the particles. So if we increase the temperature, then we increase the number of particles that have the correct amount of energy needed. If they have sufficient energy when they collide with each other, it's more likely to be effective. Plus, if they're hotter, so we increase temperature, they're going to collide more often because they're moving around more often. So if they're moving faster, they're going to collide more often, okay? So we've only put the explanations down as one way. So here I've got the faster the particles move, the more likely they are to collide, so the more likely they are to react, as well as the fact that we're increasing the kinetic energy of the particles. There we go. Okay, because remember, temperature and kinetic energy are related. So we're increasing the kinetic energy so more particles have sufficient energy. Okay? Therefore, we're more likely to have... Sure. And if any of you can read that, I think you are amazing. Because the handwriting just gets worse as we go along. But let's not tell anyone. Second one we're going to look at quickly is pressure. Please note, pressure only affects gases. They're going to try to trick you here. Okay, so it only affects gases. Now here, what happens is if we change the pressure of the gas, and this will be by volume, okay, it's the same as changing its concentration. If I make it go into a smaller pressure, for example, if I increase the pressure, the particles are closer together, and if they're closer together, they're more likely to hit each other. If they're more likely to collide, the chances of the collision being effective increase. That means the rate goes up. If we make the container bigger, the particles go further apart, they're less likely to collide, less likely to have an effective collision, rate goes down, okay? Now that actually works the same as with concentration. Now concentration is solution and gases. If we increase the concentration, we push more particles into the same volume, okay? Push more particles in the same volume, going to collide more often. If they collide more often, they're more likely to collide effectively, increases the rate. If I decrease the concentration, so I take particles out of the solution, there's less particles running around. If there's less particles running around, less likely to collide, less likely to have an effective collision, okay? Hopefully you guys are listening to the terms I'm using. It's all about the likelihood of collision. And the more likely they are to collide, the more likely it is to be effective, increases rate. Okay? We have a couple of more things to look at, but we're going to take a break first, and I'll see you in a couple of minutes. So, before the break, we looked at 3 of the things that can change the rate of a reaction. Now we're going to look at 3 more. The next one is surface area. Now, this is the one where you've got to be careful because surface area only affects your solids. And it's also sometimes called state of division. That's how the textbooks are now referring to it. It's called state of division. Okay. And what we're doing there is we're saying, and I'm going to show you now what we said is that if we increase, and all of these are increased, if I increase the surface area, then I increase the likelihood of collisions. But now I need to explain to you how we increase surface area because I think that's the important part here. If we have a chunk of something, so we have a big chunk of zinc or whatever, and you remember doing these little diagrams in grade 8 and 9. So there's my chunk of zinc that I put in sulfuric acid. The only particles that can take part in the reaction at the beginning, okay, are the ones on the outside, okay? If I now take this chunk of zinc and I break it up into smaller pieces, so I crush it, I put it into powder form, okay? So now we have lots of little pieces. Now, I know that these little pieces individually have smaller surface areas. However, altogether, we now have all of these particles available for bonding. The total surface area has increased. That is why we get more effective collisions and why the rate increases, because there's more particles that are available for bonding. So we're going to have more collisions, and the more collisions we have, the more likely it is to be effective. The more effective collision, the greater number of effective collisions we have, the higher the rate. Okay, so that's that one. Now, a catalyst. Catalysts are really important. Catalysts actually do 2 things. Catalysts can actually increase or decrease the rate. Depends on which one we use. At school level, we only use what is known as positive catalysts. And a catalyst will lower the activation energy, which then makes it easier and faster for the reaction to happen, which actually means, in real terms, that what a catalyst does is it allows more particles to have enough energy for the reaction to take place. That third part of the collision theory. The last one, and this is the one we can absolutely do nothing about, is the nature of the reactants. So with this one, some things are just absolutely more reactive than others. And this doesn't want to come off. So we'll just, there we go. We'll just, I have no idea what happened. It doesn't matter. So we have different types of substances just react faster. And I'm afraid there's nothing we can do. So the example there is iron oxidizes relatively slowly, while carbon or coal burns really fast. It's just the way it is. And we can't do anything about that. Okay, so let's go to a question. And we're going to do this question little bit by little bit, okay, because they're quite long. They're not like the physics ones. So what we have here is we have calcium carbonate chips added to an excess dilute hydrochloric acid solution in a flask, placed on a balance as illustrated. It's on a scale. The cotton wool plug in the mouth of the flask prevents spillage and of reactants and products, which means no gases can leave. Well, maybe the gases can leave. We'll have to see. But simultaneously, there we go, allows the formed gases to escape. So it's not going to allow liquids out, but allows the gas to leave. The balanced equation for the reaction that takes place is given. Oh, we like it when that happens, so that might not happen in your exam. If they're being particularly mean, this is a reaction we would actually expect you to be able to write once we've done acids and bases. So we have the calcium carbonate plus the hydrochloric acid goes to calcium chloride, carbon dioxide, and water. It is balanced. Yay, we like that. The gas can escape. Now, the reason why that's important, it's on a balance. That means it's on a scale. Okay, so that's actually a scale. So what this reaction is going to measure, if we're looking at values, it's going to measure how the mass of the container changes. And the mass is going to get smaller because the carbon dioxide is going to leave. Okay, we're going to get the calcium chloride solution at the bottom and inside the container, and the carbon dioxide is going to leave. Okay, so first thing we need to do is it says to you, oh, wait, look, I've just done that. Write down the name of the gas that escapes through the cotton wool plug while the reaction takes place. I'm not going to give you any time to do this. on your own because I just did it. It was the CO2, which means it's the carbon dioxide. If you write the formula, you don't get any marks. It said name it. First question, done. Okay, so now they give you this. So same thing that we did. Now it says the loss in mass of the flask and its contents is recorded in intervals of 2 minutes. Doesn't matter what it's done in time, in minutes, okay? And here's the results. So we have loss in mass, and you can see it goes there, then it goes up to here. They recorded one there, then we've got this. Then there's a little bit of a flat part, and then it does that. Okay, so there's my graph, and they recorded for 16 minutes. That's quite a long time. Okay, that's also why they recorded every 2 minutes. And now, from this graph, there is some very important information. So what I've got for you is, there's the graph. We're going to ask you 3 things. The coordinates of the point that represents the results that were measured incorrectly, how long the reaction lasted, and how long it took for 75% of the reaction to take place. So I am giving you 2 minutes. These can be quite difficult. And I'm going to give you 2 minutes to do this one, just this part of the question. And you're going to start now. So these were short answers, but they're not necessarily easy, grade 12. So the first thing asked you to give the coordinates to the point that represents the results that were measured incorrectly. So if we go back to our graph, okay, let's go back to, there we go, and we look at our graph, and I'm going to take away my pink now. The point is, can you see over here, that little piece? That's where there's a problem, because your graph showed that your mass was getting more, the loss in mass was increasing, then it stayed the same, then it increased again. That's not going to happen in a chemical reaction, okay? It'll go, what should have happened is the graph should have probably done that, okay? Because it should have got gradually smaller. It shouldn't have just done something in the middle. So that means that is the point that I need. So we look at it and we go, well, it's over here, so that's 6 minutes. And it's hard to see because of the screen, but it's actually 3.1. In a test or exam, it would be easier to see that. So the coordinates of this are 6 minutes, 3.1 grams. It's coordinates. It's unusual to ask it like that, but it's mass coordinates, X and Y. Then they ask you how long in minutes the reaction lasted. So we go back to the graph and we say, well, where did it start to go straight? Over here. So that means at this point over here, and we go, that's 10, 11, 12 minutes. So we know after 12 minutes it was finished. So it took 12 minutes. And then how long in minutes does it take for 75% of the reaction to occur? Now we've got to look back and we go, okay, well, we lost 4 grams. That means we take our calculators and we go 4 grams times 0.75 or 75 over 100. Okay, because we want 75%. That's 3. So now we say to ourselves, well, where did it get to 3 grams? That was 3 grams is over here, and that down here is 4 minutes. Okay. Not so bad. Okay, next question now says, the experiment is now repeated using hydrochloric acid. It's found that the rate of reaction increases. Explain this observation. I'm giving you a minute to explain that observation, and your minute starts now. So let's see how we did. Now remember, we increasing concentration. So now what that means for us is, how do we explain it? Well, increasing the concentration, okay, and I'm going to use square brackets for concentration, means more particles, okay, more molecules, that's also the same, more particles available for bonding. So we've got more particles available for bonding. If there's more particles available for bonding, there will be more collisions. Okay, which lead to a greater number of effective collisions. Okay, greater number of effective collisions. Thus, the rate of reaction increases. So I'm looking for, when we do an answer like this, I'm looking for the fact that there'll be more collisions, and because there are more collisions, there's a greater number of effective collisions, okay? So now I'm going to push you a little bit more. We're still the same thing. Now I want you to know, and I'm giving you a minute again to go, how would a higher concentration of hydrochloric affect the following? So you just got to tell me increase, decrease, remain the same. And your minute starts now. Okay, let's see how we did. So, if I have a higher concentration, first of all, they ask you what happens to the loss in mass per unit time. That is what happens to the reaction rate. Okay, mass per unit time is the reaction rate, and we just said that if I increase the concentration, I'm going to increase the rate. So that increases. But now we've got a good one. Total loss in mass. There's a very important thing here. It says excess dilute hydrochloric acid. This word excess is very important. What it means for me is that the hydrochloric acid doesn't determine how much product I get. The calcium carbonate does. So even if I increase the concentration of the hydrochloric acid, it's not going to change how much product I get. That is really important because then it means over here that the total loss in mass will remain the same. Okay? Remains the same. That's really, I put my dot on my I in somewhere random, we'll just leave it. That's really important because that's why they ask it, because sometimes you think, well, it's more concentrated, have to get more product. No, you don't. It's not the limiting reactant. Then they say the time for the reaction to reach completion. And you often get 1.4, number 1 and number 3 confused, and you go, well, the reaction rate increased, so it must increase in time. No. If the reaction rate increases, then this decreases. The time taken to reach completion decreases. It gets there faster. Okay? One last question, which I'm going to do with you. Now it says, apart from concentration and temperature, write down 2 other changes that can be made to increase the rates of the reaction. Well, the first one is we can add a catalyst. It's always the easiest one to put in. We add a catalyst. The second one is we can't change temperature. We're not starting with the gas, so we can't use pressure. We can't change concentration because they told us we can't use catalyst. The last one that we can look at is we can change the surface area. Okay, so we can change the surface area of the calcium carbonate. We can make it a powder. Okay, so we can take it from being chunks, big pieces, and we make it into a powder, increasing the surface area, which then increases your rate. Okay? Wow, we did a lot. Short break, and then we're going to finish off. So I'll see you in a couple of minutes. Okay, ready for the last push, grade 12s. This is really important. So now we're going to look at energy changes. I'm going to do this quickly because this really is revision from grade 11. First of all, remember activation energy is the minimum energy required for a reaction to take place. And when we have an exothermic graph, you've done the energy potential graphs before. Remember, the reactants have a certain amount of energy. We add energy to it. It gets to our activated complex, which we can't keep. It's temporary. After that, energy gets released, and then we get our reaction of our products. And delta H is the difference between the energy of the products and the energy of the reactants. And remember, delta H for an exothermic reaction is negative, because the products have less energy than the reactants. And the activation energy is the difference between the reactants and the activated complex. Okay? For an endothermic reaction, we have products which end up with more energy than the reactants. You guys know this, you've done this before. Delta H is now positive, because if I go the products energy minus the reactants energy, I get a positive number because the products have more energy. And my activation energy is still the difference in energy between the reactants and the activated complex. I like to describe the activated complex grade 12s as it's almost like it's a halfway station. When we get to that activated complex, the particles have come together, they've collided, and now they need to make a decision. Now they go, have we collided in the correct way? Have we collided with sufficient energy? And so are we now going to make products, or are we going to go back and become reactants? Okay? But you cannot take that activated complex out. It is incredibly unstable, and it has lots and lots of energy. We cannot use that activated complex. And you're never going to get asked what that activated complex formula is. Now, what a catalyst does is it changes the rate of reaction by providing an alternative route. And the reason why we have to look at that, and we're not going to look at exactly how it does it, but it it provides energy. You can think of it this way. It provides energy into the system, which makes it easier. We use positive catalysts at school. Please be careful with these definitions. A catalyst in general changes the rate of a chemical reaction without actually undergoing a permanent change. A positive catalyst increases the rate of the reaction by lowering the activation energy. A negative catalyst decreases the rate by increasing the activation energy. Now, at school level, we don't use negative catalysts. We don't do any reactions that are so fast and uncontrollable that we need a negative catalyst because they're too dangerous, okay? Industry will sometimes use negative catalysts because they need to control the reaction better. We use positive catalysts. In fact, when you did your ester prac, or if you are still going to do it, you use sulfuric acid in it, and that's a positive catalyst. It speeds up the reaction. And what it does is it lowers the activation energy. So if we go back to the graphs that I've drawn so beautifully on, if I now add in what happens to what the graph will look like if I now change and add a catalyst, okay, what happens is the only thing that changes is that. Okay, so now my activation energy gets smaller. So the little hill gets smaller. Same when I'm dealing with here. So if I get rid of all of this, because it's a mess, and we go back here, what it does is it does this. But the reactants and the products have the same energy. Okay? Great? Good. Let's do some questions. So here we have a graph. The graph below represents the energy changes that occur during the following reaction. Carbon monoxide plus nitrogen dioxide gives me carbon dioxide and nitrogen monoxide. Looking at the graph, didn't start at 0. It's unusual, but it's okay. It doesn't matter. So that's what we have. Okay, we have the reaction coordinates. We have some energy potentials. We're all very excited about this. And from that graph, we can take some readings. So we have over here, we have a whole bunch of things that I want you to calculate. Okay, and I think because I'm going to have to flip between them, I'm going to give you 3 minutes, okay, to answer these questions. So have a quick look, then I'll go back to the question, and I'm going to give you 3 minutes starting from now. So, how did we do? Good. Oh, we don't like graphs. I know, it's okay, you'll be fine. So, let's look at them. So here we've got our graph, and hopefully what you recognize is that over here, that is the energy of my reactants. Over here, that's my energy of my products. And over here, that's the energy of my activated complex. Now from here, I can do all the calculations. The first thing they asked was to calculate delta H for the forward reaction. So we look and we go, well, the energy of my products is minus 400. The energy of my reactants is minus 130. So for delta H, you always do products, final minus initial. So we're going to go minus 400 minus 170, and we get minus 230 kilojoules per mole, because those are the units we were given. And we're quite happy with that because, well, it's negative. It's an exothermic reaction. We can see it from the reaction. Now they say calculate, the activation energy, read the whole question, activation energy for the reverse reaction. So we go back to the graph and we say, well, reverse reaction means that I'm going from products to reactants. It's this. So it's the difference between the product's value and the reactant's value. So it's the 400 and the 40. Now, your activation energy actually has to be a positive value. Okay, so your activation energy, so it's easy to see this because it's going to be final minus initial. Okay, and that gives me 360 kilojoules per mole. So we're all happy with that. Now comes the fun question. It says, use the collision theory and explain why the rate increases with an increase in temperature. Has nothing to do with the graph. Didn't matter about the graph. It was just about what happens with an increase in temperature. So now remember, when we have an increase in temperature, and I'm going to do this in a shorthand, okay? So if we increase the temperature, what happens here is that we are increasing the number of particles with sufficient energy. Okay? Why are we increasing that? Because the overall kinetic energy has increased. Okay? Why? Because average EK has increased. Okay? Why is this important? Because by increasing the number of particles with sufficient energy, we're going to increase the number of effective collisions. This, I'm not even sure what letter I'm trying to write over there. Okay, that's why you can't write too fast. Number of effective, there we go, number of effective collisions, which then means that we increase the rate. Okay? We could also put in here the fact that because they are moving faster, we also are increasing the number of collisions. Okay, so not only are we increasing the amount of energy each particle has, so more will have sufficient energy, but, and we probably should put that in here, we're also, let's just put it over here, we're increasing the number of collisions. They're going to collide more often. Number of collisions. I think I should have been a doctor. Okay, all happy with that? These ones, guys, go look in your textbooks. These explanations are always the same, so it makes it easier for us, okay? Now, what would the effect of a catalyst be on the activation energy? They're asking you simply to say increase, decrease, remains the same. They do not want an explanation. Not explain the effect. It says, what is the effect? Well, what does a catalyst do to the activation energy? It lowers the activation energy. Okay? Always, for what we do. Lowers the activation energy. What effect does it have on delta H? None. Delta H does not change. For you to remember this, last year you did bond length and bond energy, and hopefully you spent some time calculating how much energy is needed to break bonds, how much energy is given away when new bonds are formed. That is set for every reaction. You cannot change that, which is why delta H cannot change for a reaction. Okay, that is really, really, really important. What they could also ask you is from here, and I've seen this as well, so they say to you, redraw the graph and show on the graph what would happen to the activation energy if you lowered it. So you would draw the original graph, okay, so this would be your answer. Here's your original graph, and this was an exothermic reaction. So here's my original graph. Okay, you can put in the values if they ask you for. So we know this was minus what? 170, that was minus 400, that was minus 40, and this was potential energy and the reaction coordinate. Now, what they would want you to do is go, what does a catalyst do? And you know what? Make sure you examine the nose. That's the effect of a catalyst. Okay? And that your new activation energy would be this. Ooh, look, extra things because I can. Your new activation energy would be from there to there. It's a sketch graph. Doesn't have to be accurate unless they gave you the values, which they won't. Okay, so grade 12s. Make sure you can summarize this section into half a page and practice, practice, practice. The more you do these questions, the more you realize they are all the same. They're asking you the same thing over and over and over again. They just change the word a little bit, and it's always experimental. Okay, so make sure you know your skills because they're going to ask you how to measure. All right, grade 12s? And then the next time I see you, we're going to do equilibrium. Yay, lots of fun. Not a difficult section, you just got to pay attention. Okay, grade 12s? So I'm going to say goodbye for now, and I will see you next time.